Hello everybody and welcome to another Bentley Davey Tutors video. This is currently being filmed in the process of extreme stress about the amount of videos that we're going to have to try and release in the next couple of days, but you know what, we will try as hard as we can. This video is about the physics unit for our science units this year. And so we'll be speaking about all sorts of things, but basically we'll touch on Newton's laws and pretty much everything you need to know for the physics unit. So, last video we brought you the bells, which I've heard everybody loved and nobody found annoying at all. Now, the competition was to guess how many bells there were. I counted them when I was editing the video. I counted 60 bells.
I didn't watch the video, but I probably would have counted something off of 60.
Yeah, right. So, everybody in the comments had written 59. Now, bear in mind, my counting is probably wrong, but we're going to say that we're very disappointed in you. As the qualified counters here, you should have done better. And at least, even if I was wrong, you should have predicted that we would have been wrong.
Yeah.
But into the science. Okay.
Actually,
so,
not into the science. I'm more disappointed than Jeremy has told you. I'll be expecting an apology from every single one of you in this video.
Yeah, every person who guessed needs to write an apology.
And even if you didn't guess, I want an apology and an explanation for why you didn't guess.
All right, so now into the science. So we're going to basically cover every syllabus outcome, and that will be really cool. Right, so the first syllabus outcome is distinguish between distance and displacement. Now, I'm going to be touching on two things here, but basically, distance is scalar, whereas displacement is vector. And so what that means is that distance has just got magnitude, whereas displacement has both magnitude and direction. So we know a scalar just has magnitude, whereas a vector quantity has magnitude and direction. That means that a distance graph can only go up, but a displacement graph could move up or down. Then the next syllabus point is distinguish between speed and velocity. And this is very similar because we see that speed is scalar and velocity is a vector. So we know that speed only has magnitude, whereas velocity has magnitude and direction. So for example, a speed could be 5 meters per second, whereas a velocity would be 5 meters per second east.
The next point is contrasting the instantaneous and average speed of moving objects. So the instantaneous speed of an object at any given time is just its speed at that point of time. Whereas the average speed is the average speed for the whole journey. That's a really complicated concept there. Next is describing how velocity can be determined from a displacement time graph. So essentially here, velocity is purely displacement over time. So you get the total displacement divided by the total time and you're done. One trap though is because it's velocity, you can have some funny stuff. So as per this displacement over time graph, which Jeremy will edit somewhere.
It will either be there. Probably actually over Luke's face as well I can do, but yeah, not sure yet.
That'd be good. So as you can see on that graph, the displacement at the end is 0, which makes the velocity 0. But obviously the car has moved somewhere, but we don't have any direction. So according to its displacement, it hasn't gone anywhere. Yeah,
so what that means is, for that graph before, the velocity would actually be 0. And while that might seem a bit strange, you just have to deal with it and shut up. Right, the next syllabus point is relate acceleration to a change in speed or direction. This one is good fun. Basically, the formula for acceleration is A equals V minus U over T, where A is the total acceleration, V is the final velocity, U is the initial velocity, and T is the time that might be confusing. So let's do an example. Okay, so if we say that a car is going at 10 meters per second and then increases its velocity to 15 meters per second.
Sorry, 10 meters per second. Is that an appropriate example?
Yeah.
Okay, I'm not going to be driving on the roads whenever Jeremy's out.
Yeah. Okay. Right, 15 meters per second over the course of 10 seconds. Therefore, we say, wherever that whiteboard marker is, run. Right. We've got, that's really, A equals V minus U on T. So A equals initial velocity, which is the U, was 10. Nu is 15 on T. So then we've got A equals negative, A equals 5 on T. T we've said was 10, A equals 5 on 10. Therefore, the acceleration equals 0.5 meters per second per second. Now, I'm not sure if that was something that I was meant to talk about in our divvying up of this video, or if it was Luke, but you know what? I think I'll just do it. So if you're confused about the meters per second, Why that's the case is because these are already per seconds. So the 15 and the 10 are already meters per second, because that was our velocity. So we've already got 15 meters per second minus 10 meters per second. So that means this is actually 5 meters per second. So then we're dividing that by seconds again. So we're going to have 5 meters over seconds and then over seconds again. So that equals 5 meters per second, or you can write it as 5m times, the little dot means times, s to the negative 2. And that's just because maths, which I'm not going to explain now.
So for future reference and a reminder just to us, let's never give Jeremy another example where he has to write an S and a 5, because I cannot tell which one is S and which one is 5.
It's quite a fair point. Just deal with it. All right, Luke, this is you.
All right, so next, this is quite a complicated one, and it might take me a while to explain it. So you have to recall the unit of force, newtons. Next, you have to identify the forces that act on a vehicle in motion. So I'll just list them. We've got thrust, drag, gravity, the normal force, which Jeremy said will be explained later, friction, and air resistance.
Good question as to whether or not I actually did explain it later. I don't actually think I did, but the normal force is gravity pushes down, the normal force pushes back up. That's fine.
That's what I was thinking.
Right, my thing is distinguish between balanced and unbalanced forces. A balanced force is where the opposing forces acting on an object are equal and therefore it doesn't move. And an unbalanced force is when they are not, which means motion. Next thing, describe what is meant by the term net force and calculate the net force in familiar situations. So net force is essentially the bigger force minus the smaller force. Here's an example.
More 5s, just watch out.
I think it is actually. All right, here we go. We've got a skydiver, right? Little guy or girl falling to the ground. Oh, those legs are backwards. Right, skydiver. They're falling to the ground with 500 newtons. Oh, S00 newtons, right? The air resistance pushing back up on them could just be 50 newtons, right? We'll say, for the sake of it, it's 50 newtons. Net force is going to be net equals 500 minus 50.
Do you know the calculator?
Yes, equals 450 newtons downward. So that's why it moves. It's got an unbalanced force of 450 newtons down. Now, how this can change is if we've now got the same guy, but he's got a parachute.
You do right as an elective.
I do. Right. So now, still 500 down because it's the same. Actually, it would probably be like 501. But anyway, still similar to 500 down. But instead, we've now got 450 newtons of air resistance up because this parachute increases the air resistance. So now our net equals 500 minus 450 equals 50 newtons down. So we see it still moves, but it just moves less.
Mike's just come to the door and waved to Jeremy, but Jeremy didn't respond. So I'd just like to say sorry on behalf of Jeremy to Mike, and I would love to welcome you and say hello. The next syllabus point is stating Newton's 3 laws of motion. So firstly, the law of inertia. Secondly, F equals ma, or force equals mass times acceleration. And thirdly, the law of an equal and opposite reaction. The next point is defining the term inertia. So the law here is that an object will stay at rest or continue in uniform motion in a straight line unless acted upon by an unbalanced force. So essentially everything will keep moving unless something stops it.
Great. The next point here is relate the concept of inertia to everyday situations. So I've come up with an absolutely cracking example here that I think explains it fairly well. Say you're on a bike and you're riding that bike. You are, but then your front wheel hits a big rock and the bike stops and you get flung over the handlebars. Essentially, when you're riding the bike, you and the bike are both moving. However, when you hit the rock, it stops the bike. But what the rock doesn't stop is you. It only stops the bike. You're still moving forward. And so the reason you don't, so when the bike stops and you're still moving forward, you continue to fly forward. The reason you don't just go forever, like the law states, is because the unbalanced force of gravity makes you into the table, or into the ground.
Into the table.
Into the table, right. Okay, so that's that one. So the next point is state the equation that relates the net force to mass and acceleration. This one's pretty easy. Basically, F equals ma, where F is force, m is mass, and a is acceleration.
Next, we've got identifying some common action-reaction pairs. So according to Jeremy, this one's fun. Newton's third law is the one that can be confusing for people, and it essentially states that every action must have an equal and opposite reaction. Now, why it can be confusing is because of diagrams like this. Jeremy, do the bad diagram.
Okay. Alright, here's bad diagram. That's like a table, that's a box. And 10.
Now, Jeremy, why is that a bad diagram?
So this is a shocking diagram because what it makes you think is that when you push on something, an equal and opposite force pushes on the other side of it. And the problem with that is that would mean that that doesn't move. Is there anything else that we've got here, or do you want me to continue?
I'll let you continue. You seem to have a flow.
Okay. What it actually is that when you push on something like this, let's say this is you here, it pushes back on you. It doesn't push back on the other side of itself, it pushes back on you. So that means it moves that way, you move a little bit this way, but because you're absolutely massive, you don't really move that much. Right, okay, and so basically, a good example here is when you punch a wall.
Like Jeremy regularly does.
Yeah. You exert a big force on the wall, and then the wall
it's not a very big force.
And then the wall exerts a big force back onto your hand. That's why your hand hurts, because that force is equally applied back to your hand.
Wow, thanks for really clearing that up.
No problem.
Next, we've got explaining how inertia acts on the passenger of a car, which suddenly changes its motion. Most good drivers won't suddenly change its motion, but this more applies to when Jeremy's driving.
That's fair.
So this is the fun bit, and it's very fun because it's definitely going to be in the exam, right, cars? Essentially, the car is moving and so are the people in it. Like our bike example, the car crashes, therefore the car stops moving. You know it doesn't stop moving, you. So you fly off the seat and either hit the dashboard or the seat in front of you.
Okay, so the final thing that we're going to do here, and this will 100% be on any physics exam that you're sitting with this sort of stuff in it. The question is, explain how modern car safety features such as seatbelts, airbags, and head restraints improve passenger safety.
Sorry. Did you say 100%?
I would say so.
100%.
100%. If
If
you are sitting the same physics exam as me, I would be willing to bet money that some of this information that I'm about to give you here will be part of an answer if it is correct in the thing.
How much?
$5. All right, I'll continue. Okay, so safety things do help, obviously. So I'm going to do seatbelts, headrests, and airbags here. Seatbelts, we're going to start. So this will all be how you explain it using the forces. So seatbelts work in two ways. Firstly, they act as a restraint. According to Newton 1, when the car stops, you continue to fly forward. Seatbelts lock you in and stop you from moving, so you can't fly into the seat in front of you or into the dashboard. Secondly, according to Newton 2, F equals ma, and we know that A, which is acceleration, is equal to V minus U over T. So therefore, if T is increased, if the time that it takes to slow you down increases, then the A, the acceleration, will be decreased. And if the A is decreased, then the F, being the force, is also decreased. Therefore, seatbelts work by increasing the time that it takes you to stop or to slow down and to stop. Therefore, it lowers the force on you. Secondly, airbags. Airbags are very similar. Firstly, as per seatbelts, when you move forward, they give you something soft to hit because according to Newton 1, you'll move forward. And similarly to seatbelts as well, they increase the time for your body to slow down and then decrease the force on it as per Newton 2, as I said before. And finally, headrests. These are a bit different, but basically your chair is pushing your body forward. And your headrest means that your head is also forward, and so that your head doesn't fall back in a crash and just go back like that. Secondly, in a car crash, when you stop suddenly, your head will swing forward and then it will swing back just with how your body wants to move. And the headrest will stop whiplash as it gives your head something to hit. So that is all of the syllabus points that we need to cover for this. Luke, would you like to do a nice outro?
I would love to. So hopefully you've actually learned something, although it might be quite hard after Jeremy's explanations. So this will be the first of multiple videos coming out over the next few days as at least we go into an exam block. I would also like to give a special mention to some of our new super fans who have recently joined the channel. Just a little special mention to them as well. So keep an eye out for the next videos. If you enjoy it, give it a like, maybe say something in the comments, and also subscribe for more videos. Thank you.
And bye-bye.